Hello again. These are solutions for a second problem set from Chapter 7. So this is a reprise of the first homework set. It's similar even-numbered problems. So all the stuff that we did last time around, we're going to do it again to make sure we understand. And I bet you were more successful for this. So maybe you're not even watching this video at all. Wait a minute. Then you wouldn't be hearing, well, never mind. So number 2, we're just really dealing with kinetic energy here. We've got a rocket, and it's got a mass of 2.9 times 10 to the 5th, kilograms, and it's going to reach a speed of 11.2 kilometers per second, which is 11,200 meters per second. So what's its kinetic energy then? A lot. Be 1/2 mass times velocity squared. So about 1.8 times 10 to the 13th. At 18 trillion joules. And that's it. That's all you have to do for that. Number 10. I think that's our next one, right? Yep. And you might go back and compare that just out of curiosity to the answers for number 3 from yesterday. The megaton Hiroshima bomb kind of problem. So at that point, the rocket would, what was the 13 kilotons? Well, you could compare those numbers, but it's comparable to, it's up there with those energy levels. All right. Number 10, we have a coin slides over a frictionless plane across an XY coordinate system, and from the origin to a point at 3,4,3,4. So that would be its displacement vector, 3,4. And you can do a little trig there. This is about 53 degrees. It seems like it's a thing that the, it'll have a magnitude of 5 meters, right? It's a Pythagorean triple. The 3-4-5 triangles come up a lot in these problems, and in a 3-4-5 triangle, 3, 4, 5, the angles are about 53 degrees and about 37 degrees. That comes up enough that you might want to just think that's a thing that you could remember. You can get it very easily, of course, just doing any inverse trig function on those numbers, right? But anyway, it's about 53 degrees. And then there's a force that's acting on it at, let's see, 2 newtons at a counterclockwise of 100 degrees from the positive direction of the x-axis. So that's our regular way of measuring angles. So the force is about 2 newtons here. And that's about 100 degrees. Or it is 100 degrees, rather. That's 2 newtons. So here, we're going to use, if it's a constant force, then we know that work is equal to the dot product of force and distance, which is force times distance times the cosine of the angle between them. So it's not just 2, if you think, oh, it's just force times distance, 2 times 5. It's not, because if the 2 Newton force were directed in exactly the same direction of the displacement, then it would be 10 joules of work. But here, since it's not quite the same direction here, we don't get the full brunt of the force, so to speak, in that direction of the displacement. So we have to multiply by the cosine of the angle between them. If this is 53 and it's 100, then we have a force of 2 newtons, displacement of 5 meters, times the cosine of the angle between these two things is 47 degrees. And that gives me, so I guess this is a little different than anything that we did yesterday, but it's not hard, times cosine of 47 degrees. Let me just make sure I'm in degree mode. I am. It's about 6.8 joules of work. And let's make sure that I'm in agreement with the book. I am. So we'll move on. Next is number 14. And let's see. Here we've got an overhead view of a box with 3 forces. We have force 1 is acting this way. It has a magnitude of 3 newtons. Force 2 is this way. Has a magnitude of 4 newtons. And what's the angle there? Angle 2, they're giving me this angle here, which is 50 degrees, which would make this 40 degrees. I'm going to use that one. And then force 3 is 10 newtons, and this is 35 degrees. And they want to know what's the net work done on the canister. Well, net work is equal to net force times displacement, and they told me this is 4 meters. So these are all constant forces, that's why I can use this. And since they're the only forces acting on it, the net force will be the direction of the displacement, right? If there's only that force and it starts from rest, then these will be in the same direction. So I don't have a cosine theta here. Again, let me explain that. If this is starting from rest, and these are the only 3 forces acting on it, then the net force, when we find the sum of all those forces, whatever direction that is, that will be the direction of the displacement, right? Because it's starting from rest. Couldn't be otherwise. So I need to find the net force here, so I'm just going to add these up like we do with vector stuff, like we've done before. So let's see, I'll start, I guess they called this force 1. So the x and y components of these. Force 1 has no x component and a negative 3 Newton y component. Force 2 has an x component of 4 cosine 40. That's about 3 point, I'll keep 2 decimal places for now. And that's in the negative direction. They're both negative because this is into the 3rd quadrant. And for sine 40, give me the y component, negative 2.57 newtons. And then the 3rd force here, both positive components, 10 cosine 35, and 8.19 newtons. And the y component, 10 sine 35 is about 5.74 newtons. I'll total those up, and let's see what we get. That'd be 5.13 newtons, and here, I think I'll do that with the calculator. Got negative 3 plus negative 2.57 plus 5.74. That's about just 0.17 newtons. Right? And that means the magnitude of that would be the Pythagorized Let's see, that's the square root of 5.13 squared plus 0.17 squared. And it's just about 5.13. So this is so small that that dominates the magnitude of that, 0.13 newtons. And now I can just do my calculation here. So net work is equal to force times the displacement. Was it 4? What number is this? 4 meters. And that's about 20 point, I'll say 20.5. 20.52, sorry, joules, not newtons. Right? And that does not agree with the book. So hold on a second. Let me see what we did wrong. What is the network? First 4 meters of displacement. I must have done something wrong adding up those components. Oh dear. I see what it is. I'll put this here. You probably spotted that, didn't you? So that's -3 is here, not here, and this is 0. So let me just recalculate that real quick. Sorry about that. So that's going to be -3. That's going to be 2. So the -3, and then this would be 3 bigger than that, right? So, sorry, let's try that again. 1,000 apologies. I'm wasting your time. 2.13 squared plus 0.17 squared. So that's about 3.8 newtons. So 3.8 times the displacement of 4, that's about 15.3 joules. And that agrees with the book, so sorry about that. Rookie mistake. All right. Next we have number 35. And I think this is the section where we have variable forces, right? I like these problems because they involve calculus concepts. So 35, the force on a particle is directed along an x-axis and given by force is equal to F sub 0 times x over x sub 0 minus 1. And we want to find the work